Today we embark on Unit 2, the materials there. If you did do the reading already and were a little confused, hopefully this will fill in any of the spots that are a little weird. The big thing to keep in mind with a lot of these definitions is that we are still talking about the difference between vector quantities and scalar quantities. Because in normal conversation, what you're used to, probably mostly in math even, is scalar quantities only. And we use a lot of vector quantities when doing our calculations. I swear to you, I had already reset this.
You just hit the pen button up top.
The pen?
Just have to click the pen button.
Right under the cursor.
But, is that right?
You have to click the
No,
pen
I don't. I should be able to write. I've been using this a long time, and I should be able to write. Now, I might have to do that,
Yeah,
but I shouldn't have to.
I'm sorry. This is a great picture. It works though.
It probably will.
Good job.
But I should be able to pick this up and write, but that's where we are today. So we're going to talk about some scalar quantities and then also their vector sort of equivalents, but of course vectors add one important thing, which is what? Direction. So the scalars that we have talked about before are like a distance. See, and then I got that little pen thing there. That's irritating the heck out of me. It's not your fault. It's just the way it is. So distance is a good example. The distance between two things is a scalar. The speed of something is a scalar. How do we calculate a speed? No, that's a description. How do we calculate it?
Meters per second.
Well, that's a unit that we might measure it in. So, but that's a good thing to keep in mind. If it's meters per second,
Distance over time.
it's a distance over a time. So we would write that like thus. We use v here because it's very similar to velocity, which we'll talk about in a moment. But it's a simple calculation. It's the distance that we go divided by the time that it takes. We're also going to have several vectors in class. We'll define each of those. Now, the part that the distance lacks is what direction are you moving in. And so once we add that, it becomes a displacement. It's really the distance between the start and end locations, including the direction. So distance and direction. Now let's say between 2 points. There are different ways that we will show this or that we'll write it. If you see a D with an arrow above it indicating that it's a vector, that's a displacement vector. We might see it X or delta X, something like that. And it could be Y or Z too, depending on what direction it is. But these all mean the same thing. Delta just means that change in it. But we often write it shorter, kind of a shorthand, and just say, well, if we start at 0, then we really don't need a delta. And books often use S or delta S. And but they all mean the same thing. They all mean this displacement. So instead of Rochester being 8 miles away, it would be 8 miles at 10 degrees west of north, say. Okay, so that's one. Now, we also then, if we're talking about our speed, but we're using a displacement, we no longer have speed, we now have a velocity. All right, I'm going to change the color. That's beautiful. I might be changing my mind about this. I wonder if I could go a little thinner. Oh, I can't do the I can't go calligraphy, but I could go crayon.
Oh no.
I don't think that works.
You literally have to do it like a crayon and scribble your words.
Yeah. Oh well. This is fun, I guess. Velocity is the change in location over time, or it's the displacement per unit time. Gesundheit. So if we write it, then we are going to use the same symbol as above, v, but now it's a vector. So when we're talking velocity, we should put the vector symbol over it. In practice, we get sloppy as we go a little bit farther on, and we just assume in every case that we're talking about velocity, and we often neglect to put the arrows above. And then this is a displacement, so any of these will do. Let's just do the x, realizing that it could be in any direction though. Time though is a scalar. We don't really talk about time having direction because it's always going one way. So we don't have to worry about the vector part there. And so let's say that we were going to Rochester and it took us 480 seconds. 6 minutes, 8 minutes. We could say, for example, that would be 8 miles, and I'm just going to simplify it, north, over 8 minutes. And so it would be 1 mile per minute north. That's how we would write the eventual thing. Well, the speed limit for most of that is 65. So if I average 60, I'm doing okay. And I will note that I get passed a lot heading out of town because I'm trying to keep going 55 to 60 and people are, oh, nope, it's, we're past the last light, so we're going. But I digress. Let's talk about what this means in a simple fashion. You guys watching on the video won't be able to see all of this. But I'll try and describe it. So I'm going to be walking around my desk here. This, of course, the board is almost due north for you guys. So I'm going to take steps, and for the sake of this, we're going to assume that each of my steps is 1 meter, and that each of my steps takes 1 second. Okay, so 1, 2, 3, 4. How would I describe my speed? How far did I go? 4 meters. How long did it take? 4 seconds. So if we divide my distance by my time, 1 meter per second. How would my velocity differ from that? Which would be, so how would I say it?
1 meter per second
East. 1 meter per second east, okay? 1, 2. Same questions. What's my speed?
2 meters over 2 seconds.
Meter per second still, 1 meter per second.
South.
South for velocity. And I could go around. So here, I'm going to start up here again. We're going to do this a little broader problem. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1 meter per second is my speed. What's my velocity?
0.
Why?
Because you didn't actually move.
My displacement is 0.
What would happen if you stopped over there? You have to
1,
figure out.
2, 3, 4, 5, 6. So still speed of 1 meter per second, but now I'd have to find the hypotenuse.
Roughly.
With 2 square root of 5, what's square root of 5 in decimal? It's 2 point something, so it'd be 4 point something meters at whatever angle that happened to be over the 6 seconds. So it'd be around 0.6 or 0.7 meters per second in that direction.
So you would write that on the top?
The direction?
Yeah.
Yep, direction usually would go, well, it's going to go with the vector component of this. So it'd go along with my displacement. Let's talk about this. Okay. How would we describe the speed of this? How would we figure it out?
Circumference.
So the circumference of this circle
And over one rotation.
divided by the time it takes to do a full rotation. How would we describe the velocity of this? Oh, and so would I expect a constant basically, or something that's changing a lot for speed?
Well, constant speed.
Pretty constant. I mean, it's going around in about the same amount of time all the time. Yeah, within my human capabilities, it's pretty close to constant. What about the velocity? Yeah.
Would you do like the number of times you make goes on the circle over, like that would be the distance over the time?
Let's see, right? So if I'm looking at, I can should be able to draw a circle up here. Let's pretend that's the circle. Let's make it nice and easy, so it'll be, did I just do that? Nope. Let's call it, for the sake of simplicity, the radius is 1.0 meters. And let's say that it was taking 3.142 seconds per revolution. I just put that number up there randomly. So if we want to find the speed, we'd find the distance that it's traveling, which is 2 times pi times the radius. So 2 times pi meters. Put that in meters. And then the time is 3.142 seconds. So what would my speed be? 2 meters per second. 2.0 I could even say. Meters per second. How would I describe the velocity?
Would it be infinite or zero?
Oh, it's like where you stop and then where it started, where it stopped.
Could be. So, go ahead, Hannah.
Like it depends on like where you start and where you stop.
So if I started counting here and I stopped after one circumference,
So
it'd be 0.
It'd be zero.
What if I went here?
25.
It'd be like a displacement thing.
Yep, so what is the displacement?
Distance plus.
2 meters north.
2 meters, twice the radius.
North.
North, divided by what? Half of this. What if it were here? You'd have to find the distance, straight line distance from here to here. What if it were here?
You'd have to use trigonometry.
So what this is showing is what we have talked about up above and what we talked about going around the bench here is average velocity. Average velocity takes the difference between 2 points and calculates how far is it, divides the time that it takes. So that's where that writing it as a delta x is kind of good. That's called an average. It doesn't take into account what's happening moment to moment, only what happens in total. If we're looking down at the circle, what might be more interesting, depending on our application, is to look at that moment by moment. That actually is calculus to get that. Yes, Bob?
So then, would it be totally, your answer would be totally different if like you start at one point and did it, swung around like 20 times and then stop, or
So,
swung it around like half?
Well, if I stopped at the same point, it wouldn't be it'd be 0 for average velocity, and the average speed would be the same too.
But
It'd
when
be,
you stopped, like, you started here, you stopped here, but you did like so many locations in between.
then it would probably be that it would be that distance divided by however long it took me to get there, which could be a long time. Could be a long time, yeah. but the distance wouldn't have changed. So that's average, but, oh shoot. Now, if I want to just pick a point, say this point, and I want to say, what is the instantaneous velocity? Well, now I have to know what direction is it going at that point. Let's say that overall it's rotating that way. What direction would it be moving at that point? Straight down at that moment. What about here? Kind of to the side like. What about here? So now we can go back and rely on the speed. If we're looking at it each moment, it's moving at 2 meters per second, and we could define that distance. What am I drawing here? What do I call those lines? They're vectors, but there's a special word for them. They touch this circle at only one point. So the velocity is actually, the instantaneous velocity is actually the tangent to the curve at any point. And then if we found the average speed and we kept that, that would be its velocity down in this case, or sort of to the side light. So my point is there's a difference between instantaneous and average velocity. Many times here we'll be talking about average velocity. We'll be looking at it over the span of a few seconds, and we just sort of have to acknowledge, well, it could do different things during that. The last term we're going to talk about is acceleration. Acceleration is the rate of change of velocity. It's a vector. How do we write rate of change of velocity?
Meters per second per second?
It's meters per second. And let's look at how we get that. If we're looking at how quickly does velocity change. So if we're looking at velocity changing, we'd write that as a change in velocity, delta V, over t. And if we want, just to make sure, especially since we'll use it a lot in questions, what this delta V means, whatever you see delta, it's always the same sort of calculation. It's the final value minus the initial value, which means it could be negative. And then that's over time. And as Thomas said, looking at units, we're going to use meters and seconds and kilograms for almost all of our calculations. It's easy enough to use kilometers and hours or whatever for speed, but once we get into other things, we have to be pretty consistent with that. So if we look at units, the delta V here has units of meters per second. It's a velocity minus another velocity. So that'd be meters per second. And then we have units of seconds on the bottom because of time. When we divide those, we don't cancel the S's. This is the keep it, change it, flip it thing. So we keep the top, we change it to a multiplication, and then we flip the bottom. So instead of seconds over 1, we get 1 over seconds. So the two ways we can write this that are common and acceptable are meters per second, which I like because it reminds me what it's doing. It's saying the change in meters per second in velocity every second. Or if we combine it like this, we also write it, and this is the more common way to see it, meters per second squared. But this is what it means. It means we're changing a certain amount of meters per second every second. We are not going to get real complicated, at least in calculation of this. We can use these vectors, which I do want to highlight that if these two are in different directions, one of them's got to be negative and one of them's got to be positive. And that changes what happens to our acceleration. we're mostly going to be trying to simplify things to look at them in one dimension. When we have to, when we get something at an angle, we split up the vectors, and then we treat each dimension separately, and we'll see why through labs. But we should be able to discuss more complicated situations like this one. Okay, I'm going to try and get this around again. Pretty darn even speed, right? What's the acceleration? How do you know? Is the velocity changing? Why is the velocity changing, Thomas?
Because it's changing angle of direction.
And velocity is a vector. So if I'm changing my direction, even if I'm not changing my speed, I must be accelerating. Next chapter is all about force, and so I'm not going to go into a lot of detail with that, but basically when a force is applied, you have an acceleration. You've probably all seen this. This is going to wait until next chapter. Force is equal to mass times acceleration, one of Newton's laws, Newton's second law. If there's a force, there is an acceleration. So if there's a force, there's a change in velocity. If there were no force, this wouldn't be going in a circle, right? It would just continue in a straight line. But something is applying a force, namely the string. So consider that. If we're go back to my drawing here, we're changing the velocity here at all of these points. The string is applying the force, and from down here, this sort of implies that they're in the same direction because there's no other vectors to change the direction. What direction am I applying force on this thing as I'm spinning it?
Inward. Outward.
It's like
Consider. Here is my string with the thing. Outward must be pushing. Strings suck at pushing. I'm pulling with the string. In what direction do I pull? In. The force has to be in, which means the acceleration has to be in as well, because that's the only direction I can affect it there. Let's look at what this means based on what we said down with the definition here. If it's the change in velocity. So let's take two velocities, one after the other. So I'm going to take my downward velocity, and I'm going to take my next one that was going to the right. Here's V initial, V final. My acceleration is the thing that makes it go from one to the other. So from initial to final. That's what acceleration is. It's the vector that gets it from one to the other. We're not going to treat it that way. I just present it that way, so another way to think of the acceleration, and especially in relation to velocity. But that's the acceleration due to the force that I'm applying through the string that's causing the velocity to change. If it were outward, if I were pushing outward, it would just keep going outward. But it doesn't. If we have a circle, and let's say we've got a tiny blue dot in the middle. Well, that'll represent Earth. And since we've got a black moon coming up, you didn't probably know that, but that's for another time. If the moon is going around like so, let's say that suddenly the Earth ceases to exist. Not even that it blows up, it just ceases to exist. Because if it blows up, this wouldn't work. This wouldn't be the same. It's something that can't actually happen. But let's just say, poof, it's gone. Sucked into an alternate dimension, I don't know. What direction, if the moon is traveling this way around, what direction is the moon now going to go? It's going to continue in the direction that it was moving already, which is the tangent line. If I had a force going outward on this because of gravity, well, wouldn't it just go like that normally? But it doesn't. It actually curves back in, which is saying the force must be pulling it that way, just like a string. Just to be clear, not that way. Good. We're going to pause it there. That's enough for us now to do that first problem set. We've got a little bit of time to work on it.